Let's see the concepts of vector calculus. So you might have solved a lot of problems on, you might have heard the word differentiation, partial differentiation, right? Differentiation or partial differentiation. Okay, what is the difference between this differentiation when we go for partial differentiation, when we go for differentiation? We have been saying that regression is a kind of a it's a function, right? Y equal to mx plus c. It means y is a function of a variable x. Y is a function of a variable x. So if you want to optimize these parameters like m and c, if you want to optimize the parameters m and c, you have to find out the differentiation, which will help us in finding out the optimized values for m and c, right? So when this y is dependent on a single variable, then we apply differentiation. If the same y is dependent on multiple variables like x1, x2 and xn, then you apply partial differentiation. Okay, so simple differentiation, partial differentiation. If the function, this machine learning function or the regression function, if this y is dependent on a single variable x, then you try to apply only differentiation is sufficient to find out to optimize that particular function. Okay, and if it is dependent on multiple variables, if this function f is expressed as a combination of multiple variables, then we go for partial differentiation. So little about differentiation, some rules in differentiation. You all are well versed with those. Let's quickly see, or maybe we can directly solve a problem in finding out the differentiation. Derivative of a simple function. Suppose I have a function y equal to 2x plus 1 whole power 4. I'm asking you to find out the derivative of this function f. Okay, y equal to f of x equal to 2x plus 1 whole power 4. So find out the derivative of this function f of x, right? So how do you find out for this? Maybe directly we can solve it, but I will teach you after that how you do it using chain rule or product rule. So y equal to fx plus c. So I have to find out dy by dx. I want to find out dy by, for this is nothing but this power has to come here, 4 into 2x plus 1 whole cube into then derivative of this inner function 2x plus, that is 2. So this becomes 8 into 2x plus 1 whole cube. 8 into 2x plus 1 whole cube. This way you can directly solve. But that, what is the actual rule here to, what are the actual rules in differentiation for finding out the derivatives? If you have a function y equal to f of g of x, if you have a function y equal to f of g of x, then you want to find out derivative y bar, that is f of g of x whole bar. This is nothing but how, what can you tell me what is the derivative for this f of g of x? Can someone tell me what is the derivative for this? We have a function f of g of x. I want to try to find out the derivative of this. Okay, correct. F of, right, sorry, this is nothing but f dash of g of x into g of x. Okay, first you find out f dash of g of x, then g dash of x. This way you can find out the derivative of this. So g of x, you keep it aside, just keep it like that. First find out f dash of x, then internal for this you find out the derivative into g dash of x. True. Suppose you have a function, you have a function y equal to f of x into g of x. F of x into g of x. What is the derivative of this? So f of x into g of x. bar. So I want to find out derivative for this. So how to find out derivative for this function? F of x into g of x whole bar. It's simple. Yeah. Keeping f dash of x into keep g of x constant. Here keep f of x constant into g dash of x. Right? Using this we can find out the derivative. Okay, so this way, so another simple one, I think this I need not explain, is f of x plus g of x. Somebody asked you to find out derivative of this. So it is simple as f dash of x plus g dash of x. Nothing new in this. So using these techniques, can you now try to find out this derivative of this y equal to 2x plus 1 whole power 4? Right? So maybe I can write here f equal to 2x plus 1 and g equal to f power 4. G equal to f power 4. See, I have represented as a function of f of g of x. Right? So this y is nothing but g of f of x. So I want to find out y dash. That is, for this it will be g dash of f of x as it is. Okay, into f dash of x. So g dash is f power 4. What is derivative of power 4? That is 4 into f cube, f power 3 into f dash of x. F of x is 2x plus 1. Derivative with respect to x is 2. So this is 8 into f power 3. So 8 into our f value is 2x plus 1, 2x plus 1 whole cube. So save it the same answer. Okay. So this is a few simple rules. These three rules are sufficient for learning derivatives. Let's go for now partial derivatives. Okay, we're going a little quick because nothing is new for you here. We're just revising the formulas which exist in partial derivative. I already explained you, if the function y, okay, this function y, if it is dependent on only one variable, dependent on only x, then we apply differentiation. If the same function y is dependent on multiple variables, or it is expressed as a function of multiple variables like this x1, x2, x3, so on, xn, in this case you have to do partial differentiation. Okay, you have to apply partial differentiation. So you find out partial derivatives. So what are the rules here in partial derivative? Differentiation we represent dy by dx, but in partial we represent dou y by dou x. The representation is different. Here we made dy by dx, right? Dy by dx, whereas here we give dou y by dou x. Okay, partial derivative is given by, it is known as dou, you just I tilted one, y by dou x. So how do you find out now, given a function, what is the partial derivative? Maybe you can see an example, then we might go for a formulas. So we have a function, f, which is represented using two variables x and y, that is x plus 2y cube whole square, x plus 2y cube whole square. So can you tell me what is the partial derivative of this function f with respect to x and with respect to y? Okay, we will see the formulas, but just give an attempt, try to find out the partial derivative of this function f. So dou f by dou x, similarly dou f by dou y. So what are those two values of partial derivatives of this function f with respect to x and y? So here, when you do partial derivative, when you're doing with respect to x, the other variable will act as constant. The other variable will act as constant. Whereas when you do this partial derivative with respect to y, x will act as constant. X will be constant and y will be, you have to do find out derivative of y. Yes, somebody has given 2x plus 2y cube. Okay. That is for dou f by dou x. True. What about dou f by dou y? Okay, let's see. Right. When you're doing with respect to right. Yeah. So when you do with respect to x, let's see. Let's see. Yeah. Maybe you are right. Let's see. Dou f by dou x. So I'm doing this with respect to x. So this one, this is function of x. So it will be 2 into x plus 2y cube power 1 into derivative of only x here. Derivative of only x. So df by dou x will be 1. So this becomes 2 into x plus 2y cube. This is the partial derivative of this function f with respect to only x. Why it is 1? Because again I have to find out the derivative of this x. So derivative of x, partial derivative of x is 1. When you do with respect to y, dou f by dou y, see how it becomes. Again, this is a function, so it will become 2 into x plus 2y cube into 1 into, now you do it only for y, x remains constant. So for that is 2y cube, we have the parameter as 2y cube, x, derivative, partial derivative of x with respect to y becomes 0 because it's constant, 2y cube. So this becomes 2y cube means 6y square. So this is nothing but 12x plus 2y cube into y square. 12x plus 2y cube into y square. Whereas with respect to x, it is 2 into x plus 2y cube. Okay. I hope you got idea how we are trying to solve this. Partial derivative, when you're finding differentiation, partial derivative with respect to x, y should act as constant. Since it is a function, maybe what some of them replied, their answer is true when it is not a function. Let me give an example here. Let's take a simple example and see it. See, if the function is simply like this, x square plus 2y cube. Okay. In this case, your partial derivative with respect to x will be here 2x and here 6y square. That's it. You don't have this function power n. Okay. It's simple. If you have a function x power n, its differentiation nothing but n into x power n minus 1. This is the formula you might have studied before. When you have a function x power n, its differentiation will be, or partial derivative with respect to x also can be n into x power n minus 1. That's what we did in the previous problem. So when I had this function as 2x plus 2y cube whole square, it's a function power n, right? So let's see some rules in partial derivative. This is very important because gradient is, I'll tell you what is gradient before we go. We'll try to see few equation or formulas. Tell me what is the partial derivative for dou by dou x of f of x into g of x. I have function. What is the partial derivative for this? What is the partial derivative for f of x into g of x? So when I try to find out the partial derivative of dou by dou x, f of x into g of x, it's simple. Here you try to find out dou f by dou x of f of x, dou f by dou x, dou f by dou x into g of x as it is, into g of x as it is, plus when you find out with respect to y, it is dou f by dou g by dou x. So here it will be f of x as it is into dou g by dou x. This way, that's what we have done in the previous case. How we have tried to solve it using partial differentiation. Okay. So let's see other one. What is the dou by dou x of a function if I have f of g of x, same thing, f of g of x. How do you find out partial derivative for such functions? Dou by dou x of f of g of x. Can you guess this? F of g of x, dou by dou x of, This case is simple. I am trying to find out derivative with respect to x. I am putting y as constant, this g as constant, and I am trying to find out derivative with respect to g. I am trying to put f as constant. But here, how do you find out? So you find out dou f by dou g into dou g by dou x. You first find out derivative of f with respect to g, and then find out derivative of g with respect to x. Okay, we'll see a few simple examples to understand this. And the very important here is chain rule. Okay, we have a function. What is this chain rule? So you have a function f of x1, x2. F is a function which is dependent on two variables x1, x2, and these two functions, these two variables x1, x2 are represented as functions of t. Maybe I will say f is nothing but some sign like this. F is nothing but I have sin t plus cos t. So this is x1. This is x1. Similarly, I have xt. I have 2 sine square t. So I have two variables x1, x2. They are functions of t. And f is a function of these two variables x1, x2. Okay. In such cases, we apply chain rule. Understand once again, we have a function f which is expressed as two variables, which is using two variables x1, x2. And inside each this variable x1, x2 are functions of t. Are functions of t. Then you apply chain rule. Now, how do you find out the partial derivatives for these functions which are having two variables x1, x2, and in turn each variable x1, x2 is a function of t. It is something like this. x1, x2, where x1, comma x2 are functions of t. So dou f by dou x1. Okay, dou f by dou x1 into dou x1 by dou t plus dou f by dou x2. So first I am doing with respect to x1. I am finding out the derivative of f function with respect to x1, multiplying with that x1 function with respect to t, plus same the function f with respect to x2 and the same x2 function with respect to t. This is your derivative of a function. Let's see a small example applying chain rule. Tell me what is the answer. Yes, that is dou f into dou x1 and dou x1. So given example f of x, or let f only, f equal to x1 square plus 2x2. F equal to x1 square plus 2x2. F is a function dependent on two variables x1, x2. Now x1 has some value. X1 is nothing but sin t and x2 is nothing but cos t. That's what we said. X1, x2 are variables. X1, x2 are variables which are dependent on the functions of t. Functions of t. Right? So let's try to solve this. So first find out df by dx1, dou f by dou x1. So the derivative is given like this. So derivative of this function with respect to x1 means x2 is constant. What is derivative of x1? x1 square, it is 2x1 into, and let me neatly, 2x1 into, now this derivative of x1 with respect to t. What is derivative of sin t? Derivative of sin t. So it is cos t plus, now dou f by dou x2. Now find out derivative of this function f with respect to x2. x1 is constant 0, 2x2 it becomes 2, x2 goes. Now that x2 with respect to t. So what is derivative of cos t? It is minus sin t. Minus sin t. So you want to find out the derivative of x1 with respect to t and x2 with respect to t here. So you get here, what is x1 value? Sin t. When I submit here, it becomes 2 sin t cos t minus 2 sin t. Okay, 2 sin t cos t minus 2 sin t. This is your partial derivative by using chain rule. So given a function, this is very important. I'll repeat this once again. Chain rule is base. Actually, we have to study about Jacobian. Before we go for Jacobian, it's very important for us to understand about this chain rule. Okay, so I'm saying we have a function f. We are going for partial derivatives only when this function f is dependent on multiple variables instead of a single variable. So this is dependent on x1, x2, xn, and each of these x1, x2, xn are dependent on some other variable t. Then we apply this chain rule. How we find out this derivative? We try to find out derivative df by dt, partial derivative. This is nothing but dou f by dou x1 into dou x1 by dou t plus dou f by dou x2 into dou x2 by dou t, so on like this. So you have till n, so plus dou f by dou xn into dou xn by dou t. This is your chain rule. If you find out, that is your partial derivative. That is the differentiation of partial derivative of this function f, which is a variable of t. Let us make it little advanced here. Suppose we have function f which is dependent on single variable t. That's okay. If they are dependent on two variables, advanced version, little advance of this chain rule. Here I am saying f is a function of x1, x2, and both x1, x2 are functions of t. Let's take a simple example. Yes, and write this chain rule. Let me remove this once again. So chain rule, you have a function f which is dependent on only two variables, and x1, x2 are dependent on t. In such case, derivative of with respect to t will be dou f by dou x1 into dou x1 by dou t, dou f by dou x2 into dou x2 by dou t. Now, suppose the point here is, if this function is okay, normally x1, x2 function f is dependent on two variables x1, x2. Each of these x1 and x2 are dependent on two variables s and t. If they are dependent on two variables s and t, okay, now how you find out? So you have to find out derivative of f with respect to t, which is normal, how we have written here. This is same. No change in this. It is same as this. Same way you have to do it for dou s. So dou f by dou x1 into dou x1 by dou s plus dou f by dou x2 into dou x2 by dou s. Okay. So here in this simple case, function f dependent on two variables x1, x2, both x1, x2 dependent on a single variable t. And here I am having only one function, remember, I am having only one function f1. Second case, you have one function f1, it is dependent on two variables x1, x2. Each of these two variables x1, x2 are dependent on two more variables s and t. Instead of one t, they are dependent on s and t, this case. Now let's take the another case. Advanced more will make it little complex. Same chain rule will try to apply. If you have see, I said there is a function f1 which is dependent on two variables x1, x2. Both these x1, x2 are dependent on s and t. Suppose like this, you have multiple functions f1, f2, f3, so on, fn. You have multiple functions, so on, x1, x2. All these functions f1 to fn are dependent on two variables x1, x2. Each of these x1, x2 are dependent on s and t. Okay, so instead of having one function, we are having multiple functions here. right? So let us introduce the term Jacobian, or maybe gradient first. Okay, so you are given a function, uh, you are given a function f, which is depend on two variables x1, x2, right? The gradient is nothing but collection of partial derivatives, of function f with respect to x1 and x2. Okay, little more, if we say collection of partial derivatives of f function f with respect to x1, x2 represented as a vector form. In a vector, if you represent those values in a vector form, so given a function, whatever we have seen till now, if you represent that as a vector form, that vector is called as a gradient. So I will indirectly say gradient is nothing but a collection of partial derivatives of that function f. Collection of partial derivatives of the given function f with respect to all the variables. Like if here it is dependent on two variables x1, x2, so this is called gradient. Now question is simply, let's solve one problem. Tell what is the gradient for this function. Find out the gradient for a function f, which is given as minus 2x1 plus x2. That's it. x1, x2 are not dependent on any other variable. So you have to find out gradient. Gradient is nothing. Again, you find out dou f by dou x1 and also find out dou f by dou x2. Represent them as a vector form like this. Dou f by dou x1, dou f by dou x2. If you represent them as a vector form, that is called a gradient. Gradient is nothing but the collection of partial derivatives of the function f with respect to the dependent variables like this x1, x2, x1. What is dou f by dou x1 minus 2? Dou f by dou x2, it is 1. So the gradient of this function can be written as minus 2, 1. This is as a represented as a vector. So this is called your gradient. Okay, this is called your gradient. It's also called as, we'll go for next term, that is Jacobian. Let's see what is Jacobian. Right. Gradient is collection of partial derivatives of that particular one function. Collection of partial derivatives of this function x1, which is dependent on two variables x1, x2. Jacobian is nothing but collection of partial derivatives of not one function, all the functions f1 to fn. Okay, collection of partial derivatives of all the function f1 to f1, f1 to fn with respect to all those variable x1 to xn. Okay, let's make it simple. I will tell you with simple example. Try to understand what is Jacobian. It's a collection of partial derivatives of all the functions. Okay, with respect to all the variables. Let's make a simple example. Given f1, function f1 is given as minus 2x1 plus x2. Function f2 is given as x1 plus x2. Find out the Jacobian matrix. Jacobian matrix for this given functions f1, f2. Two functions are given and you have to find out the Jacobian matrix. First one, if I ask you what is gradient, gradient is represented like this. Reverse triangle x, f, gradient of f1. So gradient of f1 is minus 2, 1. Similarly, gradient of f2, that is x1. Okay, gradient of x with respect to f2 is nothing but, if I do it with respect to x1, it is 1, with respect to x2, it is 1. Okay, these are two gradients of these given two functions f1, f2. When you're asked to find out Jacobian, it is nothing but if you represent these two as a matrix form. So minus 2, 1, 1, 1. This is called your Jacobian matrix. Okay, now let's try to understand in general case. Suppose what is the Jacobian? Suppose you have two vector valued functions f1, f2, which are dependent on two variables x1, x2. Okay, you have two vector valued functions f1, f2 dependent on two variables x1, x2. Then you find out the partial derivatives You find out the partial derivatives of both f1, f2 with respect to x1, x2, represent them in a matrix form. How do you find out? Let's find out dou f1 by dou x1, dou f by dou x1. Next, dou f1 by dou x2. This forms your gradient of f1. Similarly, dou f2 by dou x1, dou f2 by dou x2. This is another gradient. If I represent them as a single matrix, this is your Jacobian matrix. I am writing a simple case. Okay, if you try to little make it complex, you have f1 represented as functions of x1, x2. What if each x1, x2 are represented of functions of t? See this. You have function f1 which is dependent on two variables x1, x2. Both x1, x2 are dependent on t. Similarly, you have function f2 which is dependent on two variables x1, x2. Both are dependent on t. In this case, your Jacobian will be something like this. Dou f by dou x1 into dou x1 by dou t. We have seen this already. Chain rule. Dou f by or maybe f1 specifically, x2, dou x2 by dou t. Next, dou f1 by dou f2 by x1 into dou x1 by dou t plus dou f2 by dou x2 into dou f2 by dou x2 by dou t. By dou t. So this way you try to form the Jacobian. Okay, you have to apply chain rule always. We also see the advanced version. What if this both x1, x2 are dependent on s and t? So your Jacobian matrix size increases. Okay, now you try to solve and tell me what is the Jacobian matrix. Find out. Let's see an example. Find out Jacobian matrix for function f and g represented as f is given as f is a function of x comma y, that is 3x square y, and g is a function of x comma y, which is given as 2x plus y power 8. Find out the Jacobian matrix. Simple case, here x and y are not dependent on any other variable. Can you try this and tell? It's, I know, difficult to do, but please try at your end with some pen and paper and try to find out what is the value. Right? Let's try to solve. So this is a simple function. So I have to first find out dou f by dou x. Dou f by dou x is, this is y is constant. So 3x square it becomes 6xy. Next, find out dou f by dou y. This becomes 3x square. Y terms get removed. Y terms get, because the derivative with respect to y is 1. So this is over. Now find out dou g by dou x. So this is 2 because y terms become 0. Similarly, dou g by dou y. Dou g by dou y. If you do this with respect to y, x becomes 0. Y power 8 is 8 into y power 7. So you got now 4 variables. Represent them as a matrix. So 6xy, 3x square, 2, 8, y power 7. This is your Jacobian matrix. Okay, so till here it is sufficient for us to understand the optimization techniques. We have already seen where we are going to use these partial derivatives. We are mainly going to use this in regression and optimization. We use partial derivatives widely in optimization techniques. We have one problem in regression, so we are trying to apply optimization in regression using gradient descent. So there we'll be using this partial derivative concept. We will try to find out the derivatives of the function. In regression, you are trying to form an equation like this. We will try to optimize this. So we will see how we can use the concept of partial derivatives in optimizing the regression equations. Okay.